Bismillahirrahmanirrahim. In our last classes, we had discussed about the application of Gauss's law. In today's class, we will discuss about another application of Gauss's law, and that is the differential volume element. But this application slightly differs from the previous applications because in this application we will not directly find the value of the electric flux density. Rather, we will get some information that will help in defining the divergence. Apart from this application doesn't possess any symmetry. So how can we apply the Gauss's law to such application? So let's discuss about the differential volume element. We are now going to apply the methods of Gauss's law to a slightly different type of problem, one which doesn't possess any symmetry. So if a problem doesn't possess any symmetry, so how can we solve that problem by applying a Gauss's law? Because for the application of Gauss's law we need symmetry. So at first glance it might seem that our problem or case is hopeless, because without symmetry a simple Gaussian surface cannot be chosen such that the normal component of the electric flux density vector D is constant or zero everywhere on the surface. In our last class we had discussed that in order to choose a Gaussian surface there must be two conditions which must be met: that the electric flux density must be constant if the electric flux density is non-zero over the surface of that Gaussian surface. So without symmetry a simple Gaussian surface cannot be chosen such that the normal component of D is constant or zero everywhere on the surface. Without such a surface the integral cannot be evaluated. There is only one way to cope with these difficulties. So there is only one way to cope with these difficulties, and that is to choose such a very small closed surface that D is almost constant over the surface. कि हम कोई ऐसा छोटा surface select कर लें जिसपे D या electric flux density almost constant हो, and the small change in D may be adequately represented by using the first two terms of the Taylor series expansion for D, and if there are any small changes, so those small changes can be represented by using the Taylor series expansion. Why do we use the Taylor series expansion for any vector field? हम Taylor series expansion क्यों use करते हैं? Remember that if we know the value of a function at a single point, then the values of that function at every point can be found by using the Taylor series expansion. I am repeating it again, that if we know the value of a vector field or if we know the value of a function at a single point, then all the values of that function at every point can be found by using the Taylor series expansion. This example also differs from preceding ones in that we shall not obtain the value of D as our answer. In this particular problem we will not find the value of the electric flux density directly, but we will find the variation of D in the region of our small surface, but instead receive some extremely variable information about the way the electric flux density varies in the region of our small surface. This leads directly to one of the Maxwell's four equations, which are basic to all electromagnetic theory. So let's discuss about this problem. I am repeating it again that in this particular problem, we will not find the value of the electric flux density directly. But here we will select a closed surface that bounds a volume. In this particular case, we will select a closed surface, a closed differential surface that will bound a differential volume and will apply Gauss's law to that closed surface. And we will find the variations of the electric flux density over that closed surface in that closed surface. So let's suppose we have the region of a vector field. That vector field may be expressed by the electric flux density, or that vector field may be generally expressed by a vector, that is A. Let's suppose we have the region of a vector field, and let us consider any point P that is shown in the next slide, located by a Cartesian coordinate system. So the value of D at the point P may be expressed in Cartesian components, that is d naught is equal to dx naught into ax plus dy naught into ay plus dz naught into az. We choose as our closed surface the small rectangular box centered at P, having sides of lengths delta x, del y and del z, and apply Gauss's law. What does it mean? Let us consider this point P. We have this point P, and this point P is actually the center of this rectangular box, having sides del x, del y and del z. So we have a small rectangular box. This small rectangular box actually represents a closed surface. So we have this closed surface which is bounding a differential volume del x, del y and del z, centered at point P. So remember that the value of the electric flux density at point P is dx naught ax plus dy naught ay plus dz naught. This is actually the value of the electric flux density at point P, and we have the region of the vector field D. So in this region we selected this small rectangular box, and as this rectangular box will approach to 0, the value of D will be almost constant. मतलब जितना इसी बॉक्स को हम छोटा करेंगे तो इलेक्ट्रिक फ्लक्स डेंसिटी ऑलमोस्ट कांस्टेंट रहेगी. इसी बॉक्स को हम जितना बड़ा करेंगे तो जो वेक्टर फील्ड है वो चेंज करेगा. And remember that the value of this vector P, the value of this vector D at point P is dx naught ax plus dy naught ay plus dz naught az. A differential sized Gaussian surface about the point P is used to investigate the space rate of change of D in the neighborhood of P. It means that if we move along the x-axis, there will be a slight change in D. If we move along the y-axis, there will be a slight change in D, and if we move along the z-axis, there will be a slight change in D. What does it mean? From this point towards the x-axis, it means that from this point towards the right side, there will be a small change in D, because here we have no symmetry. From this point P towards minus del x. Similarly, from this point towards the front face, or from this point towards the back face. Similarly, from this point towards the top face or the bottom face, there will be a small change in the electric flux density vector D, and we will represent that small change in D in our next slide by an equation. So, what is actually the Gauss's law? The Gauss's law says that the closed surface integral of the electric flux density vector D will be equal to the total charge enclosed by the closed surface. Or we can define Gauss's law as the total outward flux. This is actually the total outward flux from any closed surface S will be equal to the total charge enclosed by the closed surface S. So we will apply Gauss's law to this rectangular box. So in order to solve the left hand side, left hand side, this integral should be broken up into 6 integrals, because if we look at this rectangular box, so this rectangular box has 6 surfaces: the front side, the back side, the left side, the right side, the top side, and the bottom side. So there are 6 surfaces. So we will apply this integral to these 6 surfaces. In order to evaluate the integral over the closed surface, the integral must be broken up into 6 integrals, one over each face. So the left hand side is actually d dot ds. It will be equal to the integral over the front side plus the back side plus the left side plus the right side plus the top side plus the bottom side. So we will not go through the complex derivations in this particular case. We will not go through the complex derivations in this particular case. Rather, we will jump directly into the results. It means that after solving these 6 integrals, these are actually the main results. The closed surface integral of the electric flux density vector D, it means that the left hand side will be equal to partial by partial x of dx plus partial by partial y of dy plus partial by partial z of dz into del x del y del z. It means that by evaluating the front and the back side, we will get the small change in dx multiplied by this volume. By evaluating the left and right hand side, we will get the small change in y, the small change in the y component of the electric flux density multiplied by this volume. Similarly, by evaluating these two integrals, we will get the small change in the z component of the electric flux density. So by adding up the results, we will get this equation. Remember that here we are taking the partial derivatives. Here we are taking the partial derivatives. We are not taking the full derivatives. यहाँ पे हम partial derivatives ले रहे हैं, यहाँ पे हम full derivatives नहीं ले रहे हैं. सही है? So why do we take the partial derivatives? If we want to represent the change in a vector field along one variable, then we take the partial derivative. What does it mean? It means that यहाँ पे जो d की वैल्यू है, it is dx naught ax plus dy naught ay plus dz naught az. So this dx naught will vary or will change when we move along the x direction, or when we move along the y direction, or when we move along the z direction, there will be a change in this dx naught. लेकिन अगर हम सिर्फ along the x direction change represent करना चाहते हैं while keeping the y and z components constant, तो फिर हम partial derivative लेंगे। इसी तरह जो dy नॉट है वो along the x direction भी चेंज करेगा, along the y direction भी चेंज करेगा और along the z direction भी चेंज करेगा। लेकिन हम partial derivative तब लेंगे जब हम along the y direction change represent करेंगे और x और z components को या x और z coordinates को हम constant रखेंगे, तो हम partial derivative लेंगे। इसी तरह जब हमने सिर्फ along the z direction change represent करना हो ndz नॉट और ndz, और x और y components हमने या x और y coordinates हमने constant रखी हो, तो हम partial derivative लेते हैं। It means that कि अगर एक फंक्शन है और उसी फंक्शन में हम एक सिंगल डायरेक्शन में या सिंगल वेरिएबल में चेंज लेके आ रहे हैं और बाकी वेरिएबल्स को हम कांस्टेंट रखते हैं, तो हम पार्शियल डेरिवेटिव लेते हैं। फुल डेरिवेटिव हम तब लेते हैं जब हम x में भी चेंज लेके आ रहे हैं, y में भी चेंज लेके आ रहे हैं और z में भी चेंज लेके आ रहे हैं, तो फिर हम फुल डेरिवेटिव लेंगे। तो अगर इसी केस में हम देख लें, सो वी आर मेकिंग अ चेंज in dx with respect to x while keeping the y and z coordinates constant. इसी तरह we are making a change in dy with respect to y while making the x and z coordinates constant, and same is the case with dz. So that is why we are taking the partial derivatives, whereas del x, del y and del z simply represents the volume element of this closed surface. Del x, del y and del z simply represents the volume of this closed surface. So this equation can also be written as we know that the closed surface integral of the electric flux density is equal to the total charge enclosed, so it will be equal to this term multiplied by the volume element del v. So the charge enclosed in volume element del v is equal to this term into the volume del v. The charge enclosed, from this equation we can say that the charge enclosed in volume del v will be equal to the partial change in dx plus the partial change in dy with respect to y plus the partial change in dz with respect to z multiplied by the volume of that closed surface. So in this particular case, in this particular problem, we are not getting the value of the electric flux density directly. हम d की वैल्यू डायरेक्टली फाइंड आउट नहीं कर रहे, बल्कि हम उन स्मॉल चेंजेस को रिप्रेजेंट कर रहे हैं जो d में आ रही है along the x direction, along the y direction or along the z direction by keeping the other coordinates constant. So here we are representing those small changes in the electric flux density vector d. Now why do we need this equation? What is the purpose of this equation? Actually this equation, these equations will lead us to the definition of divergence and the Maxwell's first equation. From these equations we will get the information about the divergence of a vector field and the Maxwell's first equation. So let's discuss about the divergence. As we know that the closed surface integral of the electric flux density is equal to the total charge, and it is approximately equal to this term. From the above equation we can say that this term will be equal to the charge, the total charge enclosed divided by the volume element, or the closed surface integral of the electric flux density divided by the volume element. And if we let the volume element tends to 0, it means that if we make the volume element approaches to 0, या अगर सिंपली हम ये कहें कि अगर इसी वॉल्यूम एलिमेंट को, डिफरेंशियल वॉल्यूम एलिमेंट को हम बहुत छोटा कर लें, such that the volume element tends to 0, so we will get this equation, and this equation is much more informative equation. So we will write this equation in two separate forms. Here in this equation, this term limit del v tends to 0 q divided by del v actually represents the volume charge density, the charge per unit volume. The charge per unit volume as the volume tends to 0 actually represents the volume charge density. So we will have this equation is equal to this term plus, and the right hand side, the left hand side is also equal to the volume charge density. So this equation contains too much information to discuss all at once, and we shall write it as two separate equations. The first equation is actually the definition of divergence. We will define divergence from this equation, from this particular equation. Similarly, this equation can be used to derive the Maxwell's first equation. So for now we will discuss about this equation. Here we have taken the vector field D. If we have a vector field A, so this equation can be written as partial by partial x of x plus partial by partial y of ay plus partial by partial z of az, and it will be equal to the closed surface integral of the vector field A per unit volume as the volume approaches to 0. Whereas this vector field A could represent the velocity, could represent the temperature gradient, force, or any other vector field. Or simply we can say that this vector field A may be a member of the electric flux density family. It may be related to the electric flux density vector D family. So how can we define the divergence of a vector field A? The divergence of a vector field A is defined as divergence of A is equal to the limit del V tends to 0, the closed surface integral of the vector field A per unit volume. So the divergence of the vector flux density A is the outflow of flux, from a small closed surface per unit volume as the volume shrinks to 0. This is actually the definition of divergence of a vector flux density A. If we have a vector field A, so the numerator actually represents the outflow of flux. The closed surface integral of the vector field A actually represents the outflow of flux from a small closed surface, and their closed surface is actually bounding a volume. So the divergence is defined as the outflow of flux from a small closed surface. The outflow of flux from a small closed surface per unit volume as the volume approaches, or as the volume shrinks to 0. Now what is the physical interpretation of the divergence of a vector field? Let's suppose if the vector field represents the electric flux density D. Let's suppose if the vector field A represents the electric flux density vector D, so the divergence of D can be written as partial by partial x of dx plus partial by partial y of dy plus partial by partial z of dz. What is the physical interpretation of divergence? Let's suppose we have a bathtub, and let's suppose we have the velocity of water in this bathtub when the drain has been opened. Let's suppose we have the velocity of water in this bathtub when the drain has been opened. So, if we take a closed surface here in this bathtub, and the drain has been opened, so the net outflow of flux or the net outflow of water from this closed surface is actually zero. So the divergence is zero because the water is actually flowing outward, but the same amount of water is actually flowing inward. It means that we have this closed surface inside the bathtub. सही है, क्योंकि यहाँ पे ड्रेन भी ओपन है, पानी बाहर भी जा रहा है, बट पानी अंदर भी आ रहा है. मतलब we have the bathtub and here this bathtub is full of water. सही है. So the net outward flow of water is actually zero. When the net outward flow of water is actually zero, it means that the divergence of the velocity of water is actually zero. Because water is incompressible, we cannot compress water. When water is incompressible, so the divergence of this water will be zero because there is no net outward flow. When there is no net outward flow, so the velocity of this water is actually, the divergence of this water is actually zero. Rather, let's suppose we have air in a tire. We have a tire and let's suppose we have air inside this tire. And let's suppose this tire becomes punctured by a nail at some point. Now air is compressible. There will be net outward flow of air from this tire. When there is net outward flow from this tire, the pressure of air inside the tire will get reduced and the air will get expanded. So in this case, we have the net outward flow of air from this tire. So this tire will have a positive divergence. The air will have a positive divergence because there is net outward flow of air. So this point actually represents a source and the divergence of air will be positive. So we have a positive divergence. A positive divergence means a source and a negative divergence means a sink. So this is actually the physical interpretation of divergence. Don't confuse this example with the example of water, because if we look at this water, with the passage of time the surface of water will get reduced. So जिस टाइम पे surface of water इसी closed surface को intersect कर ले, जिस point पे या जिस टाइम पे जो water surface है वो closed surface को intersect करेगा, तो उसी point पे we will have the positive divergence, because at that point, at that moment we have the outward flow, so we will have the positive divergence when the surface of water intersects the closed surface. When the surface of water intersects the closed surface, at that moment we will have the positive divergence. Apart from that, there is no net outward flow. The drain has been opened, water is going out, but Here if we look at the closed surface, there is no net outward flow from this closed surface because the same amount of water is entering the closed surface. So there is no net outward flow, there is no source or sink. So the divergence of the velocity of water will be 0. However, as the air is compressible, there is a net outward flow of air. So the divergence of air will be positive in this case. Because here, now this tire behaves like a source. When this tire behaves like a source, when the punctured point actually behaves like a source, so we will have the positive divergence of air. So this was actually the physical interpretation of divergence. That what does actually divergence mean? We have taken the Cartesian coordinate system. So in Cartesian coordinate system, divergence is represented by this equation. If we have the cylindrical or spherical coordinate system, then in cylindrical or spherical coordinate system, the volumes are actually different. In Cartesian coordinate system, the volume is represented by del x, del y, del z. Similarly, in cylindrical coordinate system, the volume is represented by rho d phi dz. Similarly, in spherical coordinate system, the volume is represented by r square sine theta d phi uh, dr d theta and d phi. This is actually the representation of volume in spherical coordinate system. So we will have different equations of divergence in Cartesian coordinate system, in cylindrical coordinate system, and in a spherical coordinate system. These are actually the equations of divergence in different coordinate system. So it should be noted that the divergence is an operation which is performed on a vector and the result is a scalar. Remember that divergence is operation which is performed on a vector and the result is a scalar. This result is actually a scalar quantity. We took a vector quantity, we applied the definition of divergence to that vector quantity, and the result becomes a scalar. We should recall that in somewhat similar way, the dot or scalar product was a multiplication of two vectors which yielded a scalar product. जब दो vector quantities का हम scalar product ले रहे थे, so the result was a scalar product. We will discuss further about this operation later. Thank you.